Give her a big hand, please. Lauren Shorser of Nerd Nite Toronto, so also responsible for one of these shenanigans going on in our sister city, north of the border. I want to give you up the first thing. So, here you go.
Okay, thank you, Jason. Oh, that's not for me? Okay. Okay, so, ladies and gentlemen, welcome to Nerd Nite Chicago's / Lincoln Park Zoo. We are thrilled to see you all out here, and it's going to be great. So, as Jason said, my name is Lauren Shorser. I'm going to be talking to you tonight about a group of strange and wonderful beings known as cephalopods. So, for those of you who are not quite sure what a cephalopod is, oh, hang on, I have to turn this on. There we go. I can work technology, I promise. Okay, so, if you don't know what a cephalopod is, I drew up this handy-dandy little chart here. As you may be able to tell, they are invertebrates, so they don't have bones or spines or things of that sort. There are basically two groups of cephalopods, the nautiloids and the coleoids. The nautiloids, as the name implies, are all the species of nautilus in the world, which is not really that many. There's only about 6 or 7, depending on who you talk to. They are the only cephalopods that still have shells. Those shells, you've probably seen them used in jewelry and in decorative home objects and things of that sort. They're fairly interesting beings. They tend to live relatively deep in the ocean. They come up shallower to feed. They have anywhere from 40 to 90 tentacles, and that is all I'm going to say about them tonight. The rest of the cephalopods are known as coleoids, and they are divided, as you can see there. Their first group is the Vampiromorpha. So these guys have the coolest Latin name of any animal around. It is Vampirotuthis infernalis, which literally translates to vampire squid from hell. Contrary to their name, they are neither vampires nor are they squids. They are very deep-sea beings of their own order. I can neither confirm nor deny that. But I would guess no. They're their own sort of order of beings. They're also fairly interesting. We don't know a whole lot about them, and I'm not going to be talking about them tonight either. What I am going to be talking about are the remaining cephalopods. So you have the Sepioidea, also known as cuttlefish, the Toothoidea, or the squid, and the Octopoda, or the octopuses. Now, a lot of people have really only ever seen these animals on a dinner plate, and I wanted to make sure you had some context. So, right here we have calamari, in both its breaded and deep-fried version and the grilled version. This is a squid. That's the before and after. There we go, squid. Now, here we have a slightly healthier version. We've got a salad with some octopus arms, and that is the octopus before the arms were removed from the body. And over here we have another grilled item. This is cuttlefish. Yes, there we go. That's the live animal before the tentacles all shrivel up after being grilled. And so that's what they all look like. Now, I said I was going to be talking about intelligence in cephalopods, and that's often a little bit of a peculiar topic, and people ask me how I got interested. And there's sort of a twofold reason. When I was studying biology in university, I heard this really cool urban legend about an octopus. And you may have heard a similar story, but in case you haven't, I'll just give you a quick version. So there are some scientists, and they work in a lab at their local educational institution. I keep holding this too low, sorry, Laura. So they work in a lab at their local educational institution, and some of the scientists have a tank of fish on one side of the room, and there's a tank with an octopus on the other side of the room. And, the scientists have noticed that every so often when they come in the morning, 1 or 2 of the fish are missing from the tank. And it's not like they've done that thing where fish jump out and land on the table and die, because the bodies are gone. They just disappear. And this is very confusing, and it's also very frustrating, because if you're trying to study the fish and they disappear, it makes it really hard to do research. So, there's stories floating around, and someone says maybe the grad students are getting hungry at night and eating them, because apparently this is something grad students do. And they eventually decide that, we're going to set up a video camera, and we're going to turn it on every evening when we leave, and we will see what happens. So they do. And for about a week, nothing happens, none of the fish disappear, everything's fine. And then one morning they come in, and there's a fish missing, and they go, aha, now we'll know what's going on. So they take the camera, and they rewind the tape, because this was back in the olden days when we actually still had tape. So they rewind it, and what they see when they play it is that the octopus was crawling out of its tank, across the floor of the room, up into the fish tank, catching, eating the fish, and then going back home. So I heard this story, and I thought, okay, that's pretty much the coolest thing I've ever heard about any animal. And then sort of life went on, and I didn't do much more with the whole octopus cephalopod thing. But it also so happens that I'm a scuba diver, and I am fortunate enough to have encountered all of these animals at various times in the wild. And whenever that happens, it sort of makes me wonder that, oh, you know, maybe that story was true, and it actually did occur. So I decided to spend a year studying cephalopod intelligence. Now, if you want to know whether or not an animal is intelligent, you first have to know what intelligence is. And it's a surprisingly hard word to define. I know it when I see it. That was Justice Potter Stewart. He was actually talking about hardcore pornography at the time. But people have said the same thing about intelligence. So Stephen Webster, intuitively, we know what we mean by intelligence, and we feel that we recognize it when we see it. But we don't actually define it, and it's just one of those words. We all know what it means, but if I were to ask every person in this room for a definition, I would get as many different definitions as there are people here. Now, unfortunately, I can't just base a thesis on, oh, I think I know what it is. I had to find an actual definition, so I eventually, after much searching, found this. Intelligence can be defined as an animal's degree of mental and behavioral flexibility. And that makes sense. That seems to cover a lot of different things. But how do you demonstrate mental and/or behavioral flexibility? So one way is by learning something new that you did not know before, and then using what you learned to adjust to your circumstances. And cephalopods are all very good learners. Octopus, squid, and cuttlefish have all shown that they can learn things like navigating through a maze, which is not particularly impressive, but it's a good start. They've also done some problem-solving stuff, and this is where things get a little more interesting. So for octopuses in the wild, one of the things they really love to eat is shellfish. Clams, oysters, mussels, bivalves that you pop in water and boil if you're a human, and which you cannot do if you're an octopus. If you are an octopus and you want to eat a shellfish, you actually have to drill a hole into the shell and then inject venom. And that's because when they're alive, these animals in the shells are very strong, and they hold that shell closed very closely. To pull it apart, you need to weaken the muscles and then wrench it open and consume the being inside. So they have to inject venom into a particular set of muscles. Now what's interesting is that when you look at different octopuses, different ages, you'll see differences in how they drill holes in shells. Younger, and presumably younger octopuses will often drill more than one hole in a shell, and they often seem to drill more at random. Older and larger octopuses usually only have one hole drilled in the shell, and it's at the precise location where those muscles are that they need to weaken. So what you're seeing there in the wild is that the octopus is learning from its past experiences. It said, okay, so last time I was trying to eat this kind of thing, I had to drill like 5 different holes, and it wasn't until I got the last one when I could actually eat it. So this time, I'm just going to drill in that one last spot. And they do, and it works. So that kind of learning in the wild is really, really cool, both because they're learning, but also because it's a natural experience. It's not something that's artificially created in a lab. So that's kind of fun. Yes, we get that. So what they're also showing is complex learning. And this is often more arbitrary stuff. So you can take an octopus in a lab, because that's where you have to work with them, and you can give it 2 different colored balls, one black, one white. You give the octopus a reward if it chooses the black ball. You can give it nothing if it chooses the white ball, or vice versa. It really makes no difference. Point is, it's completely arbitrary. They learned that pretty quickly. What's even more impressive is that if you take a second tank with a second octopus and put it beside the first one, and just let it watch, and then test it, it'll give you the right response the first time around. I mean, a lot of people I know can't observe others and learn from them. So the fact that we're seeing this in an animal that's more closely related to snails and slugs than anything else is really, really cool. What's also quite fun about cephalopods in general is camouflage. I mean, these guys are absolute masters. They can change the color, pattern, even the texture of their skin to blend in. And I know that when I've been scuba diving, you can literally be an arm's length away and not see the animal there because they're just that good. Which is all very well and good for me to say, but I wanted you to be able to see it for yourselves. So I'm going to play a video clip in a second, and you can play the Find the Octopus game. There's an octopus in the frame of the video for the entire video. You have to find it. Here we go. Okay, I love this. Slow motion replay in reverse. No. But okay, so just no. So yeah, color, texture, pattern of the skin, everything. I mean, the only way you could see that was not algae was because it wasn't moving the same way the rest of that clump of algae was, which is really, really cool. But what does that have to do with intelligence? Basically, it has to do with vulnerability. So cephalopods in general, and octopuses in particular, are very vulnerable animals. They don't really have a shell. Octopuses have no internal structure at all except the beak they use to eat from, which means that predators love them because there's no bone, there's no gristle, there's nothing extraneous, it's just pure food. They're delightful, and generally speaking, they're not venomous, they're not toxic, they're fantastic to eat, which means that they have to do a lot of work to avoid being eaten. And that's where the intelligence comes into play, and the camouflage. In order to escape being eaten, there's a lot of different things they can do. Camouflage is the first one, of course. You also saw it running away, you saw it squirting a cloud of ink. There's also something called bluffing. So if you see a threat that it's maybe not too threatening, they do a dramatic color change, they make themselves look really big and scary looking to try and chase it off. Mimicry, you can pretend that you're a different animal by trying to resemble it, and I'm sure you can think if you can change your color and pattern, that's not too hard to do. So I'm going to play you another little clip. You'll get to see all these different behaviors, and then we'll tie that into their intelligence. The sound on this was really over the top, so I turned it off, and I'll just narrate as we go along. Okay, so hello. This is an Indonesian mimic octopus. Lives in Indonesia area, as the name implies, and tend to live on sort of sandy or muddy, flat areas. So there's not a lot of natural cover. There's not really a whole lot to blend into. So this little guy is going to go for a walk. He's probably hungry, probably wants some food, and we can just follow along and see what he does. So that's sort of normal octopus motion that you're seeing right now, and you'll see some different types of motion later on when we get to the mimicry. Okay, so crabs. And there's the bluff. So dramatic color change, going up on the arms, looking really big, and explaining to the crab that this is not a good idea to try and pinch or attack this animal. And it generally works, off the crab goes. So what you're seeing now, thank you, Shai. So it's getting windy out here. So what you're seeing is motion like a flounder. So flounders are flat fishes that also live in the area, and you can see the actual fish there. It's mimicking that motion. Most animals will not bother trying to eat a flounder. A lot of bones, not a whole lot of meat. They're not the greatest food source. So by mimicking that flounder motion, it's trying to convince the other animals not to bother attacking it. That's a fairly energy-intensive way of moving for the octopus, so it's most likely something it's doing very deliberately as a tactic of defense. Now this posture is very intriguing, and it's going to be swimming through the water much more like a fish than an octopus. So what he's doing right now, what you'll see in a second, is that that's mimicking a lionfish. So lionfish also live in the tropical Pacific, and they are extremely venomous animals. They can be very dangerous. There are not a lot of things that will bother or hunt them, and that's the lionfish. So you can see those separated rays of the fins. There's this very deliberate resemblance, even in swimming in the water rather than along the ground, where the octopus is trying to camouflage itself as a lionfish. Nice little close-up again. Hello. And here we go. So that, I believe, is a damselfish. Damselfish can be very territorial, and they are perfectly willing to attack larger animals. So the octopus here is actually mimicking a sea snake, a banded sea snake. And you'll see in a moment black and white stripes. Again, this is a fairly venomous animal, and they are known to eat damselfish. There we go, that's the snake. And if by any chance these things do not work, the octopus can just duck into the hole and escape. So the point of all this is that there are so many different strategies the octopus can use to defend itself. And there are so many choices it has to make. It has to sit there, it has to observe the situation, It has to analyze the threat that it sees and then choose the most appropriate defense. And that kind of observation, that kind of analysis, implies a very high degree of flexibility, mental and behavioral. What does it do? How does it respond? So this is a fairly good indication of intelligence in these types of animals. Now, if you want to look at something a little more concrete than behavior in terms of intelligence, you might want to look at brains. First thing about cephalopod brains is they are shaped like a donut. You can ignore the words, they're not important. They're shaped like a donut, and that tube in the middle there is actually the esophagus, which means nothing in terms of intelligence, but it does mean that if they swallow a piece of food that is particularly large or sharp, they can actually give themselves brain damage, which is kind of wild. The second thing you would notice once you get over the donut shape is the size. Intelligent animals generally have a fairly high brain size to body size ratio, which means that the brain takes up a disproportionately large amount of the total body weight and body size. If you look at cephalopods, their brains are massive. Now again, we're talking about invertebrates. Their brains are on a par in terms of size, brain to body size ratio. They're on a par with a lot of vertebrates, sometimes fish and reptiles. There are some squid that are on a par with small mammals like weasels. I mean, that's immense. Like, that's really huge brains. What's also really funky is they have a functional convergence. So structurally, the brains are very, very different from our own. You know, the donut is one thing, there are other differences. You know, we've got sort of a lump-shaped brain, they don't, all this kind of thing. But functionally, the brains work the same way. So we, as mammals and a number of other animals, like birds, have a particular part of the brain that is used for memory storage. So do cephalopods. We have a particular area of the brain associated with learning. So do cephalopods. There's all these sort of coming togethers of how the brain works, which is even more wild when you consider that there's about 600 million years of evolution between us and cephalopods. Like, 600 million years is a very long time. The fact that somehow we are using these completely different brains in the same way is a very good indication that it is possible that some of the same things are going on inside them. And what really blows my mind is the brain waves. So electroencephalograms, also known as EEGs, also known as brain waves, measure the electrical activity in a brain. Different types of animals have different types of brain waves. Mammals, or vertebrates in general, really, have fairly low-frequency brain waves. That means the waves you can see in that diagram are relatively far apart, and they're relatively short. Invertebrates, like insects, have high-frequency brain waves. So the waves are much closer together, and the peaks and troughs are much sharper and much more pronounced. If you were to look at the EEG of a cephalopod without knowing what it was, chances are you would guess it was a vertebrate, because they have that same sort of low-frequency brainwave that we do. Now, what that actually means, I have no idea. I don't think anyone does. But it's really cool, and I quite enjoy thinking about it. Play and personality. So we're getting to some stuff that's a little more controversial now. Most of what I'm going to be saying from here on in is not 100% accepted in the scientific community. I think it's really cool, so I've included it. But you might want to keep in the backs of your minds that this is not set in stone by any means. On to the fun stuff. Okay, play. So when most people think of playful animals, they're going to think of a puppy or a kitten or something that is small and fluffy and cuddly and cute. Cephalopods are neither small nor fluffy nor cuddly nor cute, but there is evidence that they play, which is kind of wild. So how do we know this? Nobody has ever seen playful behavior in the wild that we know of. It's a little hard to tell because cephalopods don't have tails that they wag or anything like that. They're fairly, what's the word? They have no facial expressions. Like, they don't have any facial expressions. It's really hard to tell what's going on in there. But they're awesome animals. What people have seen in captivity is that if they give them new objects, the cephalopods first try to eat it because that's what you do with things that are new. Most human children do this as well. And once they figure out that the object is not food, sometimes the octopuses start to play. So they will do things like squirt a jet of water at it to force it into the current of circulating water around the tank. And so the current of water carries the little toy around, and then they squirt more water at it, start it back on its journey again. So they just sort of bounce it around the tank, basically. Others have been known to go over to the pipes that pump water into the tank, and they'll clamp themselves over them and then just hold on and let the pressure build. And the pressure builds and the pressure builds, and eventually they have to let go, and they go flying across the tank. And then they swim back over and they do it again. And it's like kids at the park, and they run over to the slide, and they climb up, and they slime down, and then they run back around to do it again. It's amazing. It's really, really cool. We don't actually know how they feel about it. So we don't know if they feel that they are playing, but it looks an awful lot like play. In terms of personalities, cuttlefish, squid, and octopus have all been shown to have distinct personalities. In fact, in aquariums, this is in laboratory studies, but also just people notice in general, in aquariums, generally speaking, the staff only give names to the mammals. So if they have otters or seals or what have you, those get names, and the octopus gets a name, and that's it. The fish don't get names, the sharks usually don't get names, just the mammals and the octopus. And that's because their personalities can be very distinctive. They can be shy, they can be very friendly, well, more bold than friendly. We don't know if they like people, but they're out there either way. So it's very, very distinctive. Now again, we don't know if this directly relates to intelligence in any way, but that kind of diversity in behavior seems to imply that there's a lot going on behind the scenes that we don't really know about. Tool use. So, tool use used to be something that we thought only human beings had, and it was what separated us from the rest of the animals. And then every so often, animal researchers would say, so we saw chimps using these twigs, and they would take the twigs and bend it and shape it and modify it, and it really looks a lot like a tool. And there would be a whole outcry because other animals don't use tools, and eventually people would accept it, usually. And this sort of happened a number of times in a number of animals. But everything else that had this claim was a mammal. And then somebody said that octopuses use tools. So, what is a tool use? What is a tool? So a tool is something that is external to an animal, so not fingers. Those are part of my body, they're not a tool. It is carried, manipulated, or modified. So, if your dog sees a rock on the ground and scratches its back against the rock, that is not tool use, because the rock is just sitting there. Nothing's happening to it. So it's carried, modified, or manipulated, and then it is used to effect a change in the animal's environment. If your dog picks up the rock and carries it and then drops it, that's not really tool use, because it didn't change anything, it just picked up the rock. So I'm going to show you a little video clip of what is claimed to be octopus tool use, and we'll talk about whether or not it actually is. So that's half of a coconut shell that the octopus has, and it's just clearing out the sand. Okay, so, tool use, yes or no? I personally am not convinced because, quite frankly, I don't think the octopus actually modified its environment in any way. Whether or not it's tool use, though, it's still really, really, really cool. And this is sort of a bone of contention in the community. There's a lot of talk about whether or not it counts. So last but not least, genetics. So this is fairly new stuff, and I'm going to be quite brief with it because there's not a whole lot known yet. But basically, we all have genes, and those genes can be organized into families. Families are either groups of genes that all are part of the same process or all have similar functions. There are some gene families that are much, much larger in cephalopods than in other mollusks. And these same gene families are the ones that we know invertebrates and mammals in particular are responsible for things like learning, plasticity in the brain, so flexibility, and development of the synapses in the brain. What this means, again, we don't really know, but it's really cool, and I'm really looking forward to the rest of the research when it eventually comes out. So conclusions. Intelligence can be defined as an animal's degree of mental and behavioral flexibility. Do they have behavioral flexibility? I would say most definitely. The learning, if nothing else, and the camouflage and the defense mechanisms. Mental flexibility, most likely. Play, personality, there's a whole lot of diversity and such going on there. But whether or not they actually are and all the rest of it, the brains and the brain waves and the genes and, tool use, purportedly, we'll sort of do more research, and I'm really looking forward to finding out about all the rest of it. And that is my presentation. Do we have time for questions? We don't, because I talk too much. I'm sorry, but I'll be here later on.
Woo, thank you.